Alrighty, let's look at problem number 7 together. It's super similar to the previous problem in that we're solving for the enthalpy of a reaction. And they were specific about the units. And with this information, we know the steps that we have to take. First step would be to solve for the moles of silver chloride. And then our second step will be to get Q of the reaction, so then we can divide the two. So let's start with step 1, and we'll set up an ICF table here. And we're given the balanced reaction. It's a precipitation reaction. I'm going to write that out so you can fill out my ICF table. The reaction is balanced. It's all 1 to 1 to 1. I'm going to take the information, the fact that I have 40 mils of 0.1 molar silver nitrate, and use that to calculate my moles of silver nitrate. So 40 divided by 1,000 times 0.1, I'm getting 0.004 moles of silver nitrate. The calculation for the hydrochloric acid is pretty much the same, except it was 50 mils. So we're going to get, for that one, and you can definitely verify, but you're going to get 0.00500 moles of hydrochloric acid. Products aren't formed yet in that initial step, so I'll throw into some zeros there. Change, we got 1, so minus x, plus x, and plus x. And then I'm going to kind of do this step in my head. Since it's 1 to 1, I can kind of see what's going on. This number, the 0.004, is smaller than the 0.005. So I feel confident saying that silver nitrate is my limiting reactant. Therefore, X in this ICF table is always going to be 0.00400 moles. So that kind of allows me to skip a step. But if you don't feel comfortable doing that, then by all means, set them equal to 0 and get your smallest X value and plug that in. So we got 0.00100 moles, 0.00400 moles of silver chloride, and 0.00400 moles of nitric acid. The value that's important to us for the next step is the moles of silver chloride. Now on to step 2. We're going to focus on solving for Q. And just like the other problem, we're solving for Q of the solution. So I'm going to do the mass of the solution times the specific heat of the solution times the change in temperature of the solution. Whatever's going on in the solution is equal but opposite to the reaction itself. Organizing the information. So we have T initial as 23.40 degrees Celsius, T final as 24.21 degrees Celsius, and we have a density of 1.00 grams per mil. Since we're adding 40 and 50 mils, so we have 90 mils of solution. I got that by adding the two quantities. Then that means we have 90 grams of solution, since we can use 1 gram per mil as the density. If it's not 1 gram per mil, then go ahead and do a density calculation. I mean, sometimes they give you a slightly different number. Don't let that hold you up. You guys all know how to calculate density. And then the specific heat, they're again using the specific heat of water, the 4.184 joules per gram. And that works really well with dilute solutions because they're basically just water. So let's plug and chug. We got 90 here. And the 4.184. And 24.21. Always check how units are canceling, grams with grams, degrees Celsius with degrees Celsius. So my Q of the solution is going to be in joules. It's going to be a positive number, it looks like. So I'm getting 305.0136 joules. This is step 2. Step 3 is to divide. So we have the top number. So we're going to do delta H of the reaction. Ooh, let me hold up a second. This is Q of the solution. This is positive. So Q of the reaction is going to be negative or exothermic. Make sure you're flipping that value before you move on to step 3. So negative 305.0136 joules divided by 0.00400 moles. And for the enthalpy of the reaction, I obtained negative 76,253.4 joules per mole of silver chloride. They want it in kilojoules, and it looks like it's 3 sig figs, so I'm going to divide by 1,000 and report my final answer as negative 76.3 kilojoules per mole of silver chloride. The negative is important because that tells us it's exothermic.